Hello, this is the video about spontaneity and positional entropy. It's 16.2 video 1. Alright, so let's say I have this piece of glassware and it's got two bulbs, and in one side there's a gas that's behaving ideally, and the other side there's just a vacuum, there's absolutely nothing in there, and in the middle I have a stopper or a valve, and I'm wondering what would happen when I open this valve. Well, I think we all know, just theoretically, we know the gas would spread out until it was evenly distributed in both sides. But the question is, why does that happen? Because it doesn't change temperature when it's going from one side to the other, so it's not like an endothermic or exothermic process. There's not a reaction taking place. What's driving this process of having the gas spread out to both sides of the container? Well, the reason is, in one word, it's entropy. And our goal in this video is to learn a little more about entropy. Entropy is usually described as a state of disorder, or like the disorganization of a system, or the chaos of a system. But a more mathematical way we could think about it is the more possibilities for something to be true, the more entropy there is. So if you think about the atoms, to have all the atoms on one side, there's only one option. There's only one way that can happen. It's every single atom has to be on the left. But there's lots of ways that the atoms could be evenly distributed. And let me be a little more specific about that. So in this picture, we have lots of atoms, but let's make it a lot more simple and just think about if we only had 4 atoms. So if we only had, and this is the same system with the two bulbs, the left side and the right side. All right. So if we only had 4 atoms and we had all the atoms on the left, there's only one way that all 4 atoms could be on the left. It's if atoms A, B, C, and D are all on the left. So we call this a microstate. There's one possibility for that to be true. What about having 3 on the left and 1 on the right? Well, the individual atom that is the one on the right could be atom A, or atom B, or atom C, or atom D, and all the 3 others would be on the left. So in the arrangement of 3 on the left and 1 on the right, there's actually 4 possibilities to make that true. So there's 4 possible microstates. If we had 2 on the left and 2 on the right, then there's actually 6 ways that could be. Just which individual atoms are on which side. So like A and B are on the left, C and D are on the right. There's 6 different combinations that would make the atoms evenly distributed. And then, of course, we could go backwards and say, well, to have 3 on the right and 1 on the left, there's 4 ways, and to have them all on the right, there's only 1 way. So let's act like we have a deck of cards, and every single microstate has its own card. If we shuffled the cards and drew them randomly, it would be most likely that we would have the cards pick a card that has 2 on each side, and it would be the least likely for it to be completely on the left side or completely on the right side. And that's how nature works. Every single one of these microstates is equally likely, but since there's so many that are the same, like we wouldn't necessarily know which one we had of these ones that are the same, the one where they're evenly distributed is the most likely because there's so many options that could be. And if you expand this idea to say, well, instead of 4 atoms, what if I had a mole of atoms, right, or just a lot of atoms, it makes it even more likely that they would be evenly distributed because there would be even more possibilities for even distribution. And that one possibility of them all being on the left would be 1 chance out of way more chances. So it's not impossible for all the atoms to all be on one side, but it is very, very improbable. All right, so relating this back to entropy, the state that has the most possibilities is the state with the most entropy. right? So it has higher, we call it positional entropy, right? Let's expand this idea to describe solids, liquids, and gases. All right. So if we think of the entropy of position, if I have a sample like a mole of a solid, there's lots of ways that the atom could be arranged in a solid, because the atoms can move a little bit in their spaces, but that same amount of substance as a liquid, remember in a liquid the atoms move past each other, there are more possibilities for the atoms, more different ways the atoms could be arranged and still be a liquid than that they could be for a solid. So liquids have more positional entropy than solids. And then gases, remember gases, the atoms can move all around. So gases have even more possibilities than liquids. So entropy, we use the letter S to stand for entropy if we're just describing it as a variable. So the entropy of the solid is the least. That's what it means when it says S solid. Solids have less entropy, then liquids have a little more, and gases have the most entropy. All right, so again, entropy is usually described as just being disorder, but you can think about it mathematically if you think, how many possibilities are there for this to be true? And the more possibilities there are, the more possible positions for the atoms to be in, or just the more different options you have to have this be true, the more entropy. So gas has the most entropy, solid has the least when you're comparing the same substance. All right, let's do a few examples. Choose a substance with the higher positional entropy per mole at a given temperature. Solid carbon dioxide and gas carbon dioxide. Well, as we just learned, gases have higher entropy than liquids and solids. So if they're at the same temperature, we have the same amount of substance, the gas is going to have more entropy than the solid because there's more possibilities for how the atoms can be arranged. All right? Then we have nitrogen gas at 1 atmosphere compared to nitrogen gas at a lower pressure. All right, now if we consider the fact that we have a mole of each and the temperature is the same in each, then the only way we could have the pressure change would be to increase the volume. So we have these two gases, they're the same element, they're at the same temperature, but they have different pressures. The one with the lower pressure is going to have a larger volume. So we could say, like, if we have 5 atoms, I know technically we have a mole, they could be spread out, you know, in any way in that little box, but if it was 1 times 10 to the negative second atmospheres, that box would actually be 100 times bigger, which I don't have room to draw, but you can imagine that there's a lot, we have our 5 atoms here and our 5 atoms in a larger box. There are way more options for where the atoms can be in the larger box than in the smaller box. So the one at lower pressure is going to have a higher positional entropy because it has more options since it has more space. All right. In this question, we're asked to predict the sign of the entropy change for each of these processes. So we have to think, is entropy increasing or decreasing? Solid sugar is added to water to form a solution. All right, so we'll have our water before and after, and the water is not really going to change too much, but the sugar is changing from solid to aqueous because it's being dissolved. And just imagine sugar molecules as a solid versus sugar molecules in the aqueous state. There's more possibilities for their position when they're aqueous. So when I dissolve the sugar, I'm going from lower entropy to higher entropy. So entropy is increasing. So the sign of the entropy change would be positive because entropy is increasing when I dissolve the sugar. All right. Number 2, I have iodine vapor condensing on a cold surface to form crystals. So I'm going from gas to solid. right? So we know that gases have higher entropy than solids, all other things being equal. So if I'm going from gas to solid, I'm decreasing the entropy. So the iodine is becoming more condensed and more ordered, and it's taking up less space. And there's less options for it. So in this one, it has less entropy after this process. So the sign of the entropy change is negative.